Hello, everyone. Today, I'll present our work on automating root cause labeling of incidents in Microsoft Azure. This is a collaboration with Chetan, Richie, Gopi, Suman, and Xuchao from Microsoft. Today's clouds are organized as many different services, and when an incident occurs in the cloud, on-call engineers debug and fix the incident to restore the service functionality. And after this, they document their debugging process and the details of this incident into a postmortem report in natural language so that others can learn from the incident and cloud management can audit the incident debugging process. Across all the services in a cloud, several engineers document many different postmortem reports. And from the cloud provider's perspective, they want to analyze these reports to extract insights and reduce future incidents by aggregating to get the top root causes of specific incidents and getting the trends of specific root causes to identify any growing vulnerabilities in the cloud. Now, since postmortems are written in natural language, to perform these aggregations, engineers label postmortems with a root cause label, which can then be used by owners to query for reports with specific labels, aggregate them, observe patterns, trends from past incidents. Today, all of this is being done manually. And specifically, let's focus on the task of labeling these postmortem reports. Engineers need a taxonomy which defines a valid set of labels which can be used for labeling a report. It turns out that this manual labeling process is ambiguous because different teams in the cloud use different taxonomies. For example, Team 1's taxonomy uses the word network for network-related incidents. Team 2's taxonomy defines the label DC networking to indicate the same. And in Team N, there might not even be a relevant label to indicate network-related incidents, indicating that these taxonomies are incomplete as well. Now, these taxonomies are also a flat list of labels, which makes finding the right label very tedious, and it's very error-prone for engineers to choose the right tag. Manual labeling is highly error-prone because different engineers have different levels of expertise and different interpretations of what a root cause means, leading to erroneous choice of labels. And this labeling is also incomplete because today engineers only tag and report with one label, whereas an incident can have multiple contributing factors in the real world. So in this talk, we will focus on automating labeling of postmortems using a tool we built called AutoARTS. In a nutshell, today, the biggest problem in learning insights from past incidents is that postmortems are so lengthy for anybody to read anything from them, existing root cause taxonomies are poor, and labeling process is erroneous and incomplete. To address this, we develop a comprehensive root cause taxonomy, bootstrap labeling process of postmortem reports manually, and use machine learning to automatically label postmortems and generate succinct context for engineers to make sense of these labels. To realize this solution, we leverage the hierarchical structure of the taxonomy we built, train text encoders with respect to root cause tags, and fine-tune gap sentence summarization models to generate contexts. We also open source our taxonomy to share all the wide contributing factors we identified with others and help develop it continuously. So this is an example of a redacted postmortem report from Microsoft Azure. We also call these documents post-incident reports or PIRs in Microsoft. So these reports are treasure troves of rich debugging insights. They have so many details, including like the symptoms of the incident, what root causes were found by engineers, what steps were taken to mitigate an incident, and so on. In Microsoft Azure specifically, engineers are also required to prepare and answer at least 5 questions that start with a why to make sure the postmortem is comprehensive. These documents are written in natural language with little to no structure. These postmortems, if analyzed, can offer insights to improve the reliability of systems against future incidents by learning gaps in debugging, monitoring, etc. But because they are so long, they're often ignored, losing valuable insights. From over 600,000 postmortem reports from Microsoft, we found that they're on average 4,500 words long, which means it's not scalable to read them manually at the scale of a cloud. And they're complex. On average, about 9 engineers are involved in each incident, exchanging about 20 comments with each other. They're written by over 34,000 engineers across different teams in the cloud. They all have different degrees of expertise and linguistic styles in authoring these postmortems. And from a sample of 1.7 million postmortems, we found that manual labeling is often erroneous, where 20% of these postmortems are labeled as others, which is not even a root cause. And we found that this is incorrect. Over 29% of these labels are incorrectly assigned to postmortem reports. This is based on a manual analysis of over 1,000 postmortems. And we found that this is also incomplete because about 58% of these postmortems are labeled as others in some other high-level category. To address these issues and bootstrap root cause labeling process, we conducted an extensive multiple person-year effort by analyzing over 2,000 incidents from over 450 services in Microsoft Azure. The goal of this analysis is to identify for each postmortem all the contributing factors behind the incident and identify key context from the report for each contributing factor. And we also conduct weekly peer reviews to refine this analysis and address any issues and develop a taxonomy of contributing factors. To ensure the quality of our labeling, we make sure we involve teams that own these incidents and domain experts of the field. And we focus on the depth and breadth of the cause of an incident to identify all the factors. Our findings are regularly turned into new standards or inform updates to existing standards in Microsoft Azure to mitigate future incidents. And we constantly evolve our taxonomy by learning new factors from incidents. With this analysis, we found that over 75% incidents are caused by more than one contributing factor. On average, 4 contributing factors cause an incident, contrary to existing practice of identifying a single root cause for an incident. This is interesting and useful because it shows us that it's sufficient to address the easiest of these factors to prevent incidents in the future, as opposed to exhaustively trying to test combinations of failures, which is not scalable. Therefore, it is important that we identify all the contributing factors for an incident. As an example, let's consider a service which became unavailable after a customer pushed a load that is greater than what the service is designed to handle. We identified the following contributing factors. First, there was an inrush of load from a single customer. Then, there was no throttling on both customer and service ends, which caused high resource usage, leading to request failures with exceptions. And poor exception handling led to resource leaks. And there were no automated watchdogs to detect these symptoms or any of these resource leaks. And the team could not access the metrics during the outage because the metrics were co-located with the service. Contrast this with today's practice of labeling this incident by a human. They just simply chose service load threshold as the label for this incident, which is not wrong, but it's not sufficient. From our analysis, we found a wide variety of 346 distinct contributing factors. This table highlights the 10 high-level categories that they all fall into. We found that over 61% of incidents were caused by gaps in detection or observability, such as missing alerts, missing telemetry, and so on. And over 50% of incidents are due to authoring, and within them, over 25% of incidents are caused by recent buggy code changes that were deployed to production. And process or procedural related incidents took the longest time to mitigate on average, next to data center infrastructure related incidents. This also shows us the wide variety of perspectives to identify contributing factors, ranging from hardware, software, observability, procedural policies, performance, and so on. Now, these contributing factors are a part of our Azure Reliability Tagging System, which we call ARTS, which is now open sourced on GitHub. And ARTS taxonomy is hierarchical. It's 4 levels deep. And it facilitates easy navigation across all these hundreds of factors starting from the highest level categories to the finest granularity root causes. It is comprehensive. Every incident should have a valid tag in the taxonomy, and every tag in the taxonomy should have been identified from incidents in the past to prevent uninformed guessing of any contributing factors. This is unambiguous to enable high-quality annotations. And ARTS taxonomy is continuously evolving and is growing stable, indicating the usefulness of tags identified so far in the taxonomy. We are now able to tag more incidents than in the past without having to add a new tag to the taxonomy. While ARTS captures a wide variety of labels, we hope that the open source effort leads to a much more comprehensive version of it and a continually evolving taxonomy. But manual root cause labeling is still error prone, and our manual analysis is very expensive and cannot scale to all postmortem reports in the cloud. So to address this issue, we built a tool called AutoARTS that can automatically label a given postmortem report with all the contributing factors from the hierarchical ARTS taxonomy with the root cause classification module. And it extracts sufficient context from the postmortems for engineers to justify and make sense of these tags with the context extraction module. Note that we intentionally keep these two tasks separate because root cause labeling should be continuously evolving, and ARTS taxonomy might not have the tags necessary for a particular incident. So this separation enables experts to discover new tags based on the context that is extracted by the tool. The first task in AutoARTS is root cause classification. Since we want to identify all the contributing factors from the ARTS taxonomy, this is a multi-label text classification problem. Now, there are several challenges in identifying all the contributing factors, such as noise. Many irrelevant details are present in the postmortem, and data sparsity. Over 68% of our root cause tags have less than 10 reports labeled with them. To address this issue, we leverage the structure of the taxonomy, which can help share knowledge between tags that have the same parent in the taxonomy using a graph convolutional network. And we leverage an existing framework called HiAGM for hierarchical text classification. Now, to encode text from the postmortem reports, even though LLMs are very good at it for several classification tasks, they need large amounts of training data to encode postmortem text, which has domain-specific usages of words. For example, fabric in English means cloth, but in networking, it means something different. Which is why we train our encoder with respect to the root cause classification tags in ARTS. To understand the difficulty in fine-tuning existing language models to encode postmortem reports, we took about 110,000 postmortem reports with their original labels chosen by humans and fine-tuned variations of BERT and ExcelNet. We observed that these models cannot be fine-tuned on these reports, as we observed a test perplexity of 7.57 for BERT, which means the model is confused between 8 words to fill in a blank with 1 word. The second task in AutoARTS is context extraction from a postmortem report. Context from a lengthy report is just a snippet of few sentences to justify the root cause tags assigned to that report. The first example shows how a buggy code change resulted in an incident and its corresponding tag from ARTS taxonomy. The second shows how missing test cases caused an incident and its corresponding tags from the taxonomy. It is important to identify key context from postmortems, not only just to justify the tags that were chosen, but this context can also help engineers identify any tags that could have been missed in classification. LLMs are good at text summarization, both extractive and abstractive, but context is not the same as the summary of the entire postmortem report, as the report contains many other unnecessary details. Pegasus is a model that is trained for summarization by masking sentences out of long documents. This is particularly useful for our task because context sentences should be extracted from postmortems, and hence we chose this model, as opposed to models that generate abstract output, which cannot accurately represent the content from PIR. We leverage the context identified in our manual analysis to fine-tune Pegasus and extract context from postmortems. To evaluate our tool, we consider about 1,100 postmortems that are manually labeled with all contributing factors based on our manual analysis. And we split this data set to train and validation sets to tune the hyperparameters and train the model. And about 20% of this data set we use for reporting the results. To identify which parts of the postmortem reports that are really useful, we conducted an ablation study using random forests to identify the top-level root cause categories for each PIR. And we found that 5 whys and root cause details are the most important parts. This step is important because models have limitations on the length of text that they can contextualize, and this step enables us to use models like Pegasus by filtering postmortems to a subset of sections. For the root cause classification task, our model, HiAGM, which leverages the hierarchical structure of the taxonomy, achieves a weighted F1 score of 89.63, while HiAGM flat, on the other hand, uses a flattened version of the taxonomy where it's just a list of opaque labels, and we notice a drastic drop in the F1 scores. This experiment clearly shows us the benefits to having a hierarchical structure to a taxonomy for root cause classification. And BERT MLC uses a fine-tuned BERT model as opposed to using our custom text encoder that we built with respect to tags. And for context extraction task, Rouge score measures recall of generated context against the ground truth, and blue measures precision of the generated context against the ground truth. Our fine-tuned Pegasus model achieves scores that are comparable to state-of-the-art summarization scores on popular data sets, and outperforms centroid-based summarization techniques, for example, using BERT, and abstract summaries that are generated by large prompt-based learning models like T5. And to evaluate the utility of AutoARTS, we presented an expert with 10 postmortem reports that they previously labeled and outputs that our tool generated. For overall usefulness of AutoARTS generated context in identifying all the contributing factors, the subject rated the outputs at 4.6 out of 5, indicating that the tool is really helpful. They also indicated that none of the tool's outputs had unnecessary details from the postmortem reports in the generated context. Even for an expert, AutoARTS generated context helped them identify 2 new contributing factors that they previously missed when they were labeling the same postmortem reports. And because the relative importance of each contributing factor is subjective, we asked the subject if they think any crucial tags were missing from the classification task. And they identified that 7 out of 10 outputs had an important root cause tag missing. This clearly indicates the need for context generation in addition to blind root cause classification. Now, to summarize, today the biggest problem in learning insights from the past incidents is that postmortem reports are very lengthy, existing root cause taxonomies are poor, and labeling process is erroneous and incomplete. To address this, we develop a comprehensive root cause taxonomy, bootstrap labeling of these reports manually, and use machine learning to automatically label them and generate succinct context from them. To realize this solution, we leverage the hierarchical structure of our taxonomy, train text encoders with respect to root cause tags, and fine-tune gap sentence summarization models to generate contexts. We also open source our taxonomy to share it with others and develop it continuously. Please join us, use our taxonomy, and help us improve it by adding many more realistic contributing factors and share it with the community. Thank you.